Linux file system architecture, full educational video script. Linux powers cloud servers, AI infrastructure, Android phones, web hosting systems, embedded devices, and most supercomputers on Earth. And underneath all of it is one surprisingly elegant design: the Linux file system hierarchy. At first glance, it may look like a random collection of folders. /bin, /etc. /prop/var. But once you understand the logic behind these directories, you begin to understand how Linux itself was designed. This is not just a collection of folders. It is an operating system philosophy. A philosophy inherited from Unix decades ago. A philosophy based on simplicity, abstraction, modularity, and standardization. And this design became one of the reasons Linux conquered modern infrastructure. In this video, we are going to slowly explore the Linux file system hierarchy. We will explain why Linux starts from a single root directory, why Linux treats devices as files, why configuration files live in /etc, why logs live in /varlog, why Linux separates user data from system data, how virtual file systems like /proc and /sys work, and why this hierarchy matters when managing thousands of servers. By the end of this video, you will not only understand Linux folders, you will understand the design philosophy behind Linux itself. Chapter 1: The root directory. Show diagram. Linux file hierarchy structure. Everything in Linux begins with a single directory. The root directory, represented by a single slash. Every file, every folder, every device, every application, every process. Everything exists somewhere under this hierarchy. This is very different from Windows. Windows uses separate drive letters: C drive, D drive, E drive. Linux does not think that way. Linux creates one unified file system tree. Hard drives, USB devices, network storage, and system resources all become part of one hierarchy. This abstraction is extremely important. Applications do not need to know where storage physically exists. Everything appears somewhere under the same root. This creates consistency. And consistency is one of the biggest reasons Linux scales so well. A tiny embedded Linux device and a massive cloud server both follow the same file system philosophy. That is powerful. Chapter 2: Why the Linux hierarchy matters. Show diagram. Why Linux hierarchy matters. At first glance, the Linux hierarchy may seem like just a collection of folders. But the hierarchy reflects deep design principles. Linux organizes system files, user files, devices, runtime data, logs, applications, hardware interfaces into predictable standardized locations. This standardization makes Linux easier to manage, easier to automate, easier to scale. Imagine managing thousands of servers. Administrators need consistency. They need to know where logs are stored, where configuration files exist, where user data lives, where applications install themselves. Linux solves this using hierarchy standards. For example, logs are usually in /var/log. Configuration files are usually in /etc. User data is usually in /home. This predictability became one of the reasons Linux dominates cloud computing and server infrastructure. Chapter 3: /bin and /spin. Show diagram. /bin directory. The /bin directory contains essential command line programs. The word bin comes from binary. These are commands required for the operating system to function. Examples include ls, cp, mv, cat. Bash without /bin, basic Linux operation would be impossible. Historically, these commands needed to exist even if other file systems were unavailable during boot. That is why /bin became so important. Now let's look at /sbin. Show diagram /sbin directory. The S stands for system. /sbin contains administrative commands used mostly by the root user. Examples include fdisk, mkfs, reboot, shutdown, fsck. These tools manage disks, file systems, and system maintenance. This separation between user commands and system administration commands reflects Linux's multi-user design. Linux was built for shared systems from the very beginning. Chapter 4 /etc. Configuration philosophy. Show diagram /etc. directory. One of the most important directories in Linux is /etc. This directory stores system configuration files. If Linux were a machine, /etc. would be its control panel. Inside /etc. are files controlling network settings, DNS configuration, user accounts, services, file system mounting, security policies. Startup behavior. Important examples include /etc/password, /etc/stab, /etc/hosts. Linux administrators spend huge amounts of time inside /etc. And this reveals one of Linux's greatest strengths. Linux uses plain text configuration files. That means configurations can be edited remotely, automated with scripts, version controlled, backed up easily, searched with command line tools. This flexibility helped Linux become dominant in servers and DevOps. Because when you manage thousands of systems, automation becomes essential. And Linux was designed for automation. Chapter 5 /home and /root. Show diagram /home directory. The /home directory stores user data. Each user gets a separate personal directory. For example, /home/Gary, /home/Alice, /home/Bob. Inside these directories are documents, downloads, desktop files, videos, pictures, user application settings. Linux carefully separates user data from system files. This improves security, stability, multi-user support. If one user damages files inside their own home directory, the operating system itself can still remain intact. This separation became extremely important in enterprise systems. Now let's look at /root. Show diagram /root directory. This is the home directory for the root administrator account. It is different from the root file system itself. Remember, / means the root file system. /root means the administrator's personal home directory. The root account has unrestricted privileges. Separating its environment improves security and organization. Chapter 6 Everything is a file. This is one of the most important ideas in Linux. Everything is a file. Not metaphorically. Literally. Linux treats many resources as file-like interfaces. And that leads us to /dev. Chapter 7 /dev and device files. Show diagram /dev files. Random number generators become files. This design is incredibly elegant. Instead of creating separate systems for interacting with hardware, Linux allows programs to use standard file operations. Programs can open devices, read devices, write devices, close devices, using the same interfaces used for ordinary files. Show diagram, devices as files. This greatly simplifies software development. Applications do not need to learn entirely different hardware communication systems. Everything uses a unified abstraction model. This is one of the deepest Unix ideas ever created. Chapter 8 /proc virtual file system. Show diagram /proc directory. The /proc directory is not a normal file system stored on disk. It is a virtual file system generated dynamically by the Linux kernel. /proc exposes real-time system information. Examples include /proc/pwinfo, /proc/miminfo. /proc/uptime. Linux monitoring tools rely heavily on /prop commands like ps, top, themstat internally read information from this virtual file system. And again, Linux exposes operating system internals using file interfaces. This consistency is one reason Linux feels elegant to engineers. Chapter 9 /var and runtime data. Show diagram /var directory. The /var directory stores changing runtime data. The word var means variable. This directory contains logs, caches, mail queues, databases, temporary application data. One especially important location is /var/log. This is where Linux logs are stored. If a server crashes, administrators often investigate /var log first. Logs are critical for troubleshooting, security analysis, auditing, monitoring, debugging. Modern DevOps infrastructure depends heavily on logs. Massive cloud systems generate enormous amounts of runtime data every second. And /var became the standardized place to organize that information. Chapter 10 /tmp temporary files. Show diagram /tmp directory. The /tmp directory stores temporary files. Applications use it for installers, temporary scripts, session files, caches, intermediate data. Many systems automatically clear /tmp during reboot. Linux also uses special permissions called the sticky bit on /tmp. This allows multiple users to share the same temporary workspace while preventing them from deleting each other's files. Even a simple temporary directory reflects thoughtful multi-user system design. Chapter 11 /usr user applications. Show diagram /usr directory. The /usr directory contains applications, shared resources, libraries, documentation. Utilities. Examples include /usr/bin, /usr/lib, /usr/share. Historically, /usr stood for User System Resources. Over time it evolved into one of the largest parts of Linux systems. Most installed software eventually ends up somewhere under /usr. Modern Linux distributions rely heavily on this structure. Chapter 12 /lib shared libraries. Show diagram /lib directory. The /lib directory stores essential shared libraries. Libraries are reusable code modules used by applications. Instead of every program containing duplicate code, Linux allows programs to share common libraries. This reduces disk usage, memory usage. Software duplication. Examples include C standard libraries, dynamic loaders, boot critical modules. Without these libraries, many Linux applications would fail immediately. This is one of the hidden engineering layers underneath the operating system. Chapter 13 /boot and the startup process. Show diagram /boot directory. The /boot directory contains files required during startup. Examples include Linux kernel images, grub bootloader files, Initramps images. When the computer powers on, the bootloader loads the Linux kernel from /boot. Without this directory, Linux cannot start. This chapter connects the file system directly to the operating system boot process. Chapter 14 /mnt and mount philosophy. Show diagram /mnt directory. One of the deepest Unix concepts is mounting. Linux does not use separate drive letters. Instead, storage devices become attached somewhere inside the file system tree. For example, a USB drive may appear under /mnt/USB. This unified design means everything belongs somewhere under root. Hard drives, network storage, external devices, all integrated into the same hierarchy. This abstraction makes Linux extremely flexible. Chapter 15/sys and modern kernel interfaces show diagram /sys directory. The /sys directory is another virtual file system. It exposes structured information about hardware, drivers, buses, power systems, kernel subsystems. Modern Linux hardware management depends heavily on /sys. Like /proc, it reflects Linux's philosophy of exposing system internals using file system interfaces. Final chapter: Why Linux 1. Linux did not become dominant by accident. Its file system hierarchy helped create consistency, predictability, automation, scalability, modularity. A Linux administrator can log into thousands of servers and immediately understand where things are. Logs are stored in predictable locations. Configuration files follow standards. Applications organize themselves consistently. Devices expose unified interfaces. This standardization made Linux easier to automate. And automation became one of the foundations of modern cloud computing. Today, Linux powers cloud infrastructure, AI servers, web hosting systems, Android internally, enterprise systems, embedded devices, supercomputers, and underneath all of it is this file system philosophy. Simple, consistent, modular, powerful. The Linux file system hierarchy is not just a collection of folders. It is one of the foundational designs of modern computing. And once you understand it, Linux itself begins to make much more sense.